Okay, so part one for the partial fraction expansion. So this is the case where you have a transfer function that has, or a Laplace transform that has non-repeated or simple real poles. So this is one where it looks like this. F of s is equal to 1 over s plus p1 over s plus p2. And maybe rather than writing 1, what I'm going to do is I'll write, there's really some numerator polynomial. I'll write it as num of s, like this, okay? And then what we're going to do is we're going to expand this into partial fractions, r1 over s plus p1 plus r2 over s plus p2. And if I had more poles, right, obviously I'd have more terms in this case. So the question is, how do I solve for the residues r1 and r2? Okay, well, I use this fact. If I multiply both sides, multiply the left-hand side and the right-hand side by s plus p1, okay? And then evaluate, and we're going to set s equal to minus p1, okay? So if you notice this term here, s plus p1, when I set s equal to minus p1, this term goes to 0, okay? That's what it means for this thing to have a pole at minus p1, okay? So here's the left-hand side, it's f of s, and here's the right-hand side. And so what I get is, on the left-hand side, I'm going to sort of rearrange it. So if I just look at this guy here, I get r1, because I have s plus p1 in the denominator, plus s plus p1 times r2 over s plus p2. And that's equal to s plus p1 times f of s. And I'm going to evaluate, so I multiplied both sides by s plus p1, and now I'm going to evaluate at s equals minus p1. So I do this, I go set s equal to minus p1 here. Here, set s equal to minus p1, okay? And what this does is that on the right-hand side, this term goes to 0, right? Because I don't have, right, the denominator here has only s plus p2 in it, and so I know that when I set s equal to minus p1, this goes to 0, and so that eliminates the term that involves r2. And if I had any other terms here, like an r3 and r4 or whatever, they would also be eliminated, okay? And so what I'm left with is r1 is equal to s plus p1 times f of s, whoops, times f of s times f of s evaluated at s equals minus p1. And similarly, I could write like r2 is equal to s plus p2 times f of s evaluated at s equals minus p2. Okay, so this is how I solve for the residues. All right, so that's the general form for this. Now what I'm going to do is I'm going to do an example. Okay, so again, this is example 1, so it holds for a Laplace transform that has simple poles. Okay, so here I've got y, oops, I want to use black for this, sorry. Y of s is equal to s plus 2 times s plus 4 divided by s times s plus 1 times s plus 3, and we want to find y of t, okay, by partial fraction expansion. Okay, so we'll notice that the y of s has poles at s equals 0 from this term, minus 1 from this term, and minus 3 from that term. So there's 3 poles, and they're real, and they're not repeated. Okay, so the solution to this is y of s equals r1 over s plus r2 over s plus 1 plus r3 over s plus 4. Okay, and it's easy to solve for these residues using the formula. R1 is going to be equal to s times y of s evaluated at s equals 0. Okay, because that's what the first pole is, at s equals 0. So let's do this calculation. Well, when I take y of s and I multiply by s, I eliminate this first term in the denominator. So I get s plus 2 times s plus 4 over s plus, over s plus 1 times s plus 3. And I'm going to set s equal to 0. So I get 2 times 4 in the numerator, and in the denominator I get 1 times 3. Okay, so I can say that R1 is equal to 8 thirds. So that's the first residue. And then the second two are basically the same method. R2 is equal to s plus 1 times y of s, evaluated at s equals minus 1. Okay, so I get same numerator, s plus 2, s plus 4, divided by s times s plus 3. And I'm going to evaluate this at s equals minus 1. So I get R2 is equal to minus 1 plus 2 is 1, minus 1 plus 4 is 3, divided by minus 1 plus 3 is 2, and so I get minus 3 halves. Okay, so that's R2. And then R3 is equal to s plus 3 times y of s, evaluated at s equals minus 3. And so I get s plus 2 in the numerator. Okay, s plus 4 over s times s plus 1, evaluated at s equals minus 3. R3 is equal to minus 3 plus 2 is 1, minus 3 plus 4 is 1, minus 1. And in the denominator I get minus 3 times minus 2. So I get minus 1/6. That's right. Okay, and so now what we can do is we could write what y of s is. So y of s is going to be equal to, look back on the previous page, R1 is 8 thirds. So the way I wrote it right here is it's R1 over S, R2 over S plus 1, R3 over S plus 4. So I get, I get 8 thirds times 1 over S minus 3 halves times 1 over S plus 1 minus 1/6 times 1 over S plus 3. Okay, so this is y of s. This is the partial fraction expansion for y of s. All right, so I'm almost there, and now what I got to do is to find the inverse Laplace transform for each of these terms. Okay, so the inverse Laplace transform for 1 over s is the unit step. For 1 over s plus 1 is e to the minus 1 times t, and for 1 over s plus 3 is e to the minus 3 times t. Okay. And each of these guys is really going to end up being multiplied by the unit step. So I'm going to write it like this. Y of t is equal to 8 thirds minus 3 halves e to the minus t minus 1/6 times e to the minus 3t. And the whole thing is multiplied by the unit step, u of t. Okay? So this is the final solution that I was looking for. Right, so the idea in the partial fraction expansion is that we break it into terms, simple terms that we know the inverse Laplace transform for, and then we can quickly write down the inverse Laplace transform. Okay, so that's what I get when I have simple poles. Now case 2, if I have repeated real poles. Okay, so in this case, my function f of s looks like this. Numerator of s divided by s plus p1 times s plus p2 squared. So it has a repeated root at minus p2. So we would write basically the poles are minus p1, minus p2, and minus p2. Okay, so it has 3 poles, but just 2 of them are repeated. In this case, what we're going to do is we're going to write it out like this. R1 over S plus P1. This is a simple pole, and so I use the same trick as I used before. Now I get 2 terms for the repeated pole. R2 over S plus P2 plus R3 over S plus P2 squared. Okay, so this is a P2. Okay, and then I can solve for R1 in the usual way. Then how do I find R2 and R3? Okay, turns out that R3 is the easy one. R3 is going to be equal to S plus P2 squared times f of s, whole thing evaluated at s equals minus P2. So it's very similar to what I used to solve for R1, and R2 is the tricky one. R2 is going to be equal to d ds of s plus P2 squared times f of s, evaluated at s equals minus P2. Okay? All right, so I'm going to illustrate this by example. So this is, I'll put a little box around this to show how we're going to do this. Okay, and let's do an example. And the example I picked is this guy. F of s is equal to 1 over s plus 1 times s plus 2 squared. Okay, and I'll write out the expansion. I've got r1 over s plus 1 plus r2 over s plus 2 plus r3 over s plus 2 squared. Okay, r1 is easy. R1 is going to be s plus 1 times f of s, evaluated at s equals minus 1. And so when I do this, I get 1 over s plus 2 squared, evaluated at s equals minus 1. And so that's 1 over 1 squared, which is 1. Okay. And R3 is also easy, so I'll do R3 next. S plus 2 squared times f of s, evaluated at s equals minus 2. And I get 1 over s plus 1, evaluated at s equals minus 2. So I get 1 over minus 1, so that's minus 1. And then R2 is the tricky one. I got d ds of s plus 2 squared times f of s, evaluated at s equals minus 2. So that ends up being d ds of 1 over s plus 1, evaluated at s equals minus 2. And so when I do that differentiation, I get minus 1 over s plus 1 squared. And I'm going to evaluate that at s equals minus 2. So I get minus 1 over minus 1 squared is equal to minus 1. Okay? So now we'll put together all the partial fractions the way we wrote it as r1 over s plus 1, r2 over s plus 2, r3 over s plus 2 squared. We have 1 minus 1 minus 1 as r1, r2, and r3. So we end up with f of s is equal to plus 1 times 1 over s plus 1 and minus 1 times 1 over s plus 2 and minus 1 times 1 over s plus 2 squared. Okay, and now to do the inverse Laplace transform, so these ones we already know. This one, I'll probably have to look it up on a table, and so I did that, and I found that the Laplace transform that we want is generally written in the table like this. Laplace transform of, like this, the inverse transform of 1 over s plus a squared is equal to t e to the minus at. Okay? And so knowing that, then we've got f of t here is going to be equal to 1 times e to the minus t minus 1 times e to the minus 2t minus 1 times e to the minus 2t, t here. And then this whole thing, to be careful, we'll write it like this, multiplied by the unit step, okay, to make sure that this is a causal function. Okay, so that's case 2.